Welcome to AP Physics 1. This is the first video in a sequence that will cover all aspects of the 2024 update of AP Physics 1. The focus of this video, and a great place to begin any introduction to a physics class, is talking about motion. It may seem like a very intuitive thing if you're asked what motion is, but we are going to look at some very specific ways of analyzing the motion of objects. For this video, we will be focusing on one-dimensional or 1D motion, meaning that an object will only be moving back and forth along a straight line, including up and down. To begin our analysis of motion, take a look at the ball here on the screen. As you can see, it is at some location that we can define as some origin point. Now we have defined where the object is. The X in this case stands for the position of the object, like X marks the spot. Now that the screen is back, you can see that the object is no longer where it was. It is moved to the other side of the screen. We don't know how or why it got there, just that it moved. This change in position is called displacement and is denoted by a delta x. The symbol in front of the x, as I just said, is the Greek letter delta. You've probably and hopefully seen it in other science classes. It means change in, and will be used frequently in this course. The way to determine a change in anything is to take the final value of that quantity and subtract the initial value of that quantity. So taking the final position 5 meters and subtracting the initial position 0 meters will give us plus 5 meters. This term only refers to the change in position from one point to another, and is not to be confused with distance, which is the total amount traveled by an object. Displacement is also the first use of a vector quantity, which is a type of quantity that incorporates not only a magnitude or size value, but a directional value as well. So if we were to discuss this ball having moved, we could say its displacement is 5 meters to the right. For most cases, as you'll see in the future, the use of a positive or negative sign will be an indicator of direction for most situations. Now let's take the same object from before, but this time we're going to see the motion. Okay, so now we saw the object slide from its original position to the 5 meter mark. So the displacement is the same as before, but now we know how long it took the object to get from one point to another. Using this information, we can determine the next important aspect of motion analysis. If we take the displacement of that object and divide by the change in time of the motion, we will get the object's velocity. This is another vector quantity that tells us the rate of change in the position of the object, which we calculated to be 2.5 meters per second. If the ball were to have continued moving like it was, it could be going 2.5 meters every second of the time that passed. As this motion is set up to be an unchanging or constant velocity, there would be no practical difference between the average velocity and the instantaneous velocity of the object. The difference between these two terms will appear later in the video. One last thing of note is that you are most likely familiar with the term speed. While the most common parlance tends to use speed and velocity interchangeably, there is a huge difference in physics. Velocity is a vector and therefore has a directional component, which means it can show up as a negative value. Speed is a scalar quantity, which is just a numerical value, so will not have a direction associated with it. The difference between these two terms is something to be very familiar with, as there will most likely be questions asking about either term and expects you to know the difference. Now that we've discussed objects that move at a constant velocity, we now need to understand objects that have a non-constant velocity. Again, let's use the ball at the bottom of the screen to give an example. Now with that example, it should be clear that the ball starts off slower and increases its velocity as it moves. As this ball started with a velocity of 0 and reached some velocity by the end, there is a change in velocity present. And combined with the time it's taken to go the 5 meters, we get the last major quantity needed for the analysis of motion. The change in an object's velocity over the change in time is called an object's acceleration. You can see the equation, but there is an issue with this example. If we wanted to calculate the acceleration, we don't know what velocity the ball reached. So we can't quite find the acceleration yet, but there is a small experiment we can run to learn the relationship between displacement, acceleration, and time. We're going to take our x-axis and just angle it up like a ramp. Now we're just going to see how far the object goes in certain times. Let's observe how far the object goes in 1 second. Okay, so it went 1 meter in 1 second. Now let's see how far it goes in 2 seconds. If you want to take a guess, do so now. Okay, so if you thought it would go 4 meters, then you're correct. Some of you may already be able to see a pattern, but let's do 3 seconds to see. 9 meters traveled in 3 seconds. Hopefully these numbers should shout out to you that there is a square relationship between the displacement traveled and the time it travels. What this information gives us is the first and most important equation for kinematics, the displacement curve. You can see the t in the equation is squared, showing that the time is squared. The v0 term is to account for an object that may be starting with some initial velocity. Don't worry about where the 1/2 comes from, as the explanation will lead us way off course into a tangent about calculus, so just go with it for now. Let's return to the original setup. As you can see, now that we have this equation, we don't need the final velocity to find out what the acceleration is. The initial velocity is 0, so that term is removed. Then rearrange the equation and plug in the numbers. And you should get 2.5 meters per second, or 2.5 meters per second squared. Okay, so now that we have the 3 main quantities needed to analyze motion, displacement, velocity, and acceleration, let's take a look at some situations that will give you a better idea and understanding of how these terms relate and work. Imagine a car on a long track that is already moving at a constant velocity. The driver hits the brakes. What you see is the car slowing down to a stop, which should hopefully be a normal experience. There are 2 aspects to this motion: the portion where the car is moving at a constant velocity, and the portion where the car is accelerating. These sections have to be addressed separately. When an object is moving at constant velocity, the acceleration would be 0. And if you put that into our displacement curve equation, you actually get the definition of velocity you saw earlier in the video. Hopefully you see here that the definition of velocity as I gave earlier is really just the displacement curve, but only for conditions where acceleration is 0. Moving on to the accelerating section, let's put up an arrow on the car to show the direction of its velocity. You can see that the arrow is decreasing in length as it slows, which is a kind of visual way to show that the value is decreasing. When thinking about how this car is accelerating, let's use the acceleration definition from before. I have the delta v split into its final minus initial terms for ease. If you look at just the velocity variables, in this situation the final velocity would be 0 as it stops. That means the top of the fraction is going to be 0 minus some value, which would come out to a negative number. This will make the acceleration come out negative, and if you recall from the displacement section, positive and negative can be used to define direction. This means that the acceleration vector on this car should point to the left and will remain a constant value until it stops. An easy way to remember how the velocity and acceleration vectors work is that if they point in the same direction, an object will get faster, but if they point in opposite directions, the object will slow down. The last thing to discuss in 1D motion is one specific situation that will show up frequently throughout the course: freefall. Freefall is a situation where the acceleration of an object is due to the force of gravity. We're not going to get into the nitty-gritty about gravity until Unit 3, so for now it is good enough to think of gravity as the force that pulls an object toward the ground. Freefall occurs in the vertical dimension, with up being positive and down being negative usually, and has a constant acceleration of usually some known value. On Earth, the acceleration is negative 9.8 meters per second, or meters per second squared, while other planets and moons have their own unique value. As a reminder, the negative signifies that it's in the downward direction. Instead of the usual variable for acceleration a, when we're talking about the acceleration due to gravity at a particular location, it is given the specific variable g, standing for gravitational field strength. For situations in this course, unless it is specified that an object or system is somewhere else, assume that it takes place on Earth. Let's look at some scenarios and implications of freefall. The first and most well-known thing is that if you have 2 objects that are dropped from the same height at the same time, they should hit the ground at the same time. In the absence of air resistance, which would keep the shown feather from falling as fast due to other forces, then all variables associated with either object are identical, so the time would be the same. This fact of objects falling at the same rate will be an integral component of many questions. Let's do just a quick practice calculation for the drop time of these objects. If the objects were dropped from a 10-meter cliff, how long would it take them to hit the ground? Things we can tell from this question are that the objects were dropped from a 10-meter height and ended at the ground, which is a good place to make 0 height. This shows that the displacement is -10. We know that the objects are dropped, so the initial velocity for each object is 0. And lastly, and the important part, even though it isn't mentioned in the question, you know that these objects are falling, so there is an acceleration due to gravity. And since it doesn't specify a place, assume Earth. That gives us acceleration equal to g. If we're looking for time, we should use our trusted displacement curve equation. The initial velocity is 0, so we can cancel the first term. Now we should rearrange the equation to solve for t. As a side note, you should practice doing the manipulations without numbers, as many questions will not include numbers in the future. But for now, all that's left is to plug in our known values. And there you have it. It would take both objects √2 seconds to reach the ground. That wraps up the lesson for 1D motion. Stay tuned for part 2, which will cover 2D motion. If you need more help or want to do some more practice problems, check out the companion video that goes along with this lesson. Don't forget to like and subscribe.